Okay, in this section we're going to be going through 4B, which is going to be collisions. So during a collision, objects can change their individual momenta, meaning objects might have a certain momentum going into a collision, but after a collision they're probably going to have a different momentum. And there are different types of collisions. So the first one is an elastic collision. So in elastic collisions, objects bounce off of each other. So you have two objects, sure, they run into each other and then they bounce off of each other. That would be an elastic collision. The other main type would be inelastic collisions. So in an inelastic collision, objects are going to stick together. So they start apart like this, but instead they would end up sticking together. So that would be an example of an inelastic collision. And then the last kind of way that objects can interact would be an explosion. So in an explosion, objects are stuck together initially. So objects would be stuck together initially, and then they would split apart after that. So that's the way that you can get objects interacting with each other. You can get an elastic, inelastic, or explosion, and all of those are going to cause the momentum of those objects to change. So it's important to keep in mind that when you're looking at these collisions, as long as there's no outside forces, meaning if you're only looking at just what's happening during the collision, you're negating friction, you're negating air resistance, the total momentum during a collision is conserved, meaning the total momentum remains constant. So the mathematical way of saying that is the law of the conservation of momentum. So it basically says, if you don't have any outside forces, your total momentum will stay the same. So this is the law, the way it's written. There's some new symbols. So it's basically saying the net or the total PI is equal to the net or total PF. So what does that mean? Well, let's see the first symbol. So the total initial momentum, so all the momentums added up together on the left side, so the sum of all the momenta of each object before a collision is equal to the sum of the momentum of each object after the collision. So net PI means the total momentum initially, right before a collision, and then that's going to be equal to the net PF, so the total momentum after the collision. So you're basically just adding up the momentum of each object before and after a collision. So just real quick, let's say you had two objects ran into each other. One had a momentum of 5 ns Newton seconds. One had a momentum of -3 Newton seconds for a total of, just add them together, total of 2 Newton seconds. Right? If you were to look at what would happen after the collision, let's say they stuck together, the total momentum of them together wouldn't change. It would stay constant, assuming there's no friction, air resistance. So that's what it's saying. The total momentum of all the objects added up before a collision, right, -3 and 5, is equal to the total momentum of the objects after the collision. It's just basically saying you can't create momentum, you can't destroy momentum, but you might transfer it between objects. So that's the idea. So what are the different types of interactions objects can have? in which they're going to change their momentum and realizing that momentum is conserved, meaning it cannot be created or destroyed. Okay, we're going to see a problem out with collisions. Here we go, problem. So make sure you try to solve it out first. Even if you can just get the knowns, unknowns, write out part of it, that's going to be helpful. Instead of just, seeing the solution out completely first, make sure you take an attempt. Okay, I'm going to sketch this out. So we have a 5 kilogram block, red block going at 10 meters a second to the right, runs into a 3 kilogram blue block moving at 7 meters a second to the left. The two blocks collide. Oh, I just undone some stuff. The two blocks collide, and then the blue block bounces off at 6 meters a second to the right, and it's looking for how fast the red block is moving. So quick sketch, red block, blue block, red to the right, blue to the left. This is initially what's happening. And then, let me redraw that eye. And then what do we have? So what's happening after the collision? Or what's happening finally? So we have the same two blocks, red and blue. The blue, it says, is going to the right, and we don't know what's happening here to the red. So we're looking for what's happening to that red block after. So we know a bunch of stuff. I'm going to use some notation. You don't have to use this, but I'm just using some notation to make it easier so I don't have to keep writing red over. So red, I'm just going to say, is associated with the number 1, and blue is associated with the number 2. So let's write out all our knowns and unknowns. So we know two masses. We know mass of the red is 5 kilograms. We know the mass of the blue, M2, is 3 kilograms. We know the initial velocity, so the velocity before the collision, of the red is 10 meters a second. We know the initial velocity of the blue is -7 meters a second because it's to the left. We know the initial velocity, or the final velocity, the velocity after the collision of the red. Nope, sorry, the final velocity after the collision of the blue. And then we're looking for the final velocity of the red. So the final velocity after that collision. So if you can get even there, that's definitely helpful. So picture, here are knowns and unknowns. Maybe you wouldn't write this exact notation, but something like this. So we have a bunch of masses and velocities, and we're looking to find another velocity. So this makes sense to look at the momentum of these objects. So we're actually going to do the conservation of momentum. Again, it's going to look like a lot, but it's a basic idea. So we're basically going to add up the momentum on each side. So the total initial momentum is equal to the total final momentum. Remember, momentum of one object is just m times v, so we're just going to add up a bunch of mv's together on each side. So I'm going to write it out. I'm going to do the notation. You do not need to have quite the same notation. So on the left side, net pi is equal to the total initial momentum. So mass of the red times the initial velocity of the red plus mass of the blue times the initial velocity of the blue is equal to the mass of the red times the final velocity of the red plus the mass of the blue final, should be VF1, plus the mass of the blue, the final velocity of the blue. We're looking for this right here, final velocity of the red. So basically, it looks like a lot, but it's really just adding up all the masses and velocities of each object. From here, you really just have to plug in all these numbers on the right side of the problem. So 5 times the initial velocity of 10 plus mass of 3 times the initial velocity of -7 because it's to the left is equal to the initial the mass of the red times the final velocity of the red plus mass of the blue times the final velocity of the blue, which is 6. So from here, it's really just algebra, just careful plugging in. So we get 29 is equal to 5 VFI plus 18. So we solve this out. It's going to be 11 is equal to 5 VF 1. So the final velocity of the red is going to be 2.2 meters a second. So what this says actually is, it wasn't, we couldn't have predicted it for sure, but it says the positive means it's going to the right. So they run into each other, and then after the collision, they both end up going to the right. The red's going to slow down from what it was at 10 meters a second, but it's still moving to the right technically. So this problem, it looks like a lot, but remember, just keep in mind that it's going back to the same things that have been done, for problems, a lot of problems like this. So picture knowns and unknowns, equation, and then being careful with algebra. So make sure you have this solution copied down, make sure you have the notes, and that's it for now.